This is 3.4. And it's called product and quotient rules. Okay, so this is at some point, right? I showed you that if you take, or actually, let me give you a concrete example. So let's take f of x. Let's say it's x, and then let's take another function g of x, and that's going to be x squared. So what we'll try to do is try to figure out what the if you take those two functions and you multiply them, right? What will be the derivative of that product? So take f of x, okay, times g of x, and we're trying to figure out what the derivative is. Okay, so let's do it, the way it's not supposed to be done. So the wrong way. Here we go. So we would take f prime of x times g prime of x. All right, so we have, actually let's do it here. So f prime of x equals 1, right? Because derivative of x is just 1. G prime of x. Right, so now I'm taking derivative of x squared, so that's going to be 2x. Right, so derivative of this. Okay, so now if I take these two, right, I'll have 1. That was the derivative of f of x, times 2x. So that's 2x. Okay, so of course, there's a question. That's a question mark. This is actually not right, because, well, if you take those two functions, so I have f of x. So we somehow don't know if this is correct, right? What I know is correct is that if I take these two functions and I multiply them first, and I'm taking derivative of them, so that's going to be the first function was x times x squared. Now I'm taking derivative of these, so that's x cubed, and derivative of that is 3x squared. Okay, so this is the correct answer, and it just shows us that we can't really do it this way, right? This is not right. So that does not equal this. Well, so what does it equal to? Well, that's what that product rule is about. Unfortunately, it's a little more complicated, right, than just kind of derivative of a product is a product of the derivatives, right? It's not that simple. Well, it works like this. Anyway, if I take, let me change the notation and do the dx. Okay, so I'm taking derivative of product of two functions times g of x. Okay, so what that equals to, I need to take a derivative of the first one. So let's do, how should we do this? Doesn't really matter. I'm just kind of thinking about notation, what would be the easiest. Maybe like this for now. So f prime of x. So I'm taking a derivative of the first, and I'm multiplying by the second one, times g of x. I don't like the way it's. Maybe I'll try to make it smaller so that I can fit it in one line. Okay, so one more time. So ddx. Okay, so now I have making smaller by making this bigger. So f of x times g of x. Okay, so I'll take a derivative of the first. So f prime of x. That actually doesn't matter. And I'll show you in a moment what I mean. So times g of x. So now we'll have plus. Now I don't change that first function, so just f of x times g prime of x. Okay, so it could be like this. This one version, or you could do, right, it doesn't matter whether I add 1 plus 2 or 2 plus 1, same thing. So we could do it like this, so that equals f of x times g prime of x plus f prime of x times g of x. Okay. I tend to use that first version, right? So take a derivative of the first function, multiply it by the second one, then plus, right? I'm talking about this. So take a derivative of the first function, multiply it by the second one unchanged, then the first one unchanged, derivative of the second. Okay, I tend to use that version, but it doesn't matter. Okay, so let's see how it works. So example 1. Example 1. And what we need to find is find derivative of f of x (3x squared) times sine x. Okay. So let's use the other notation, meaning, well, let me just do it. So ddx of f of x. Okay, so I'll use this notation. So ddx of 3x squared, right? So I'm taking derivative of the first times sine x plus. Now I do 3x squared, so I'm not changing that first function, times derivative of the second function. All right. Okay, so derivative of that derivative, right? I'm calculating this. So that is 6x times, let's use parentheses, sine x. Now we have plus 3x squared. Derivative of sine is cosine x. And yeah, let's leave it this way. We could factor maybe 3x, but it's not gonna make it particularly, I don't know, simpler, easier, more simplified. So let's call this the final answer. Yeah, so this is how it works. And yeah, the second rule is called the quotient rule. So that tells us how to deal with when I have two functions that are divided. Okay, so yeah, so again, right, ddx. Let's use the same type of notation, and then we have f of x divided by g of x. And yeah, so now it's important, right, how you do this, because there is a subtraction between those two expressions, two terms. So it matters that you actually do take a derivative of the first. So f prime of x times g of x, right? So that's unchanged, the second function unchanged. Now I have minus, right? That's the minus I'm talking about. And then let's extend this. And then we have f of x, right? Not changed, times g prime of x. All right, and that is divided by g of x squared. Let's do it this way, squared. Yeah, so that's the quotient rule. Let me do this, hold on. Okay, so now let's write the quotient rule here. Quotient rule. Okay, so that's the rule here. Okay, yeah, so examples. And of course, right, that g of x, let's make a little note here. The g of x cannot be 0. Cannot be 0. Okay. Okay, so example 2. And yeah, again, find derivative. And we have something like this, ddx with 5x minus 2 on the top. So 5x minus 2, and the bottom is x squared plus 1. Okay, so we have this, I was going to write that rule again, but we have it up here, right? So we have that rule here, and that's what we'll be using. So what does it say? It says take a derivative of the first function, right? So yeah, maybe, let me see, what would be the easiest way to write it, so for you to see. I think I'll just use parentheses and then the prime symbol. Okay, so I'm taking derivative of that first function, which was 5x minus 2. So we have 5x minus 2, right, derivative, times the second function unchanged, and that was x squared plus 1. Then we have minus, first function unchanged, so 5x minus 2, and then derivative of the second function. All right, and yeah, the bottom is just the second function squared, or the function from the denominator, right, squared. So x squared plus 1 squared. All right. So hopefully you guys see it. So that equals. So now we need to take those derivatives. Right, we have space, and yeah, so we go. We're here, right? So taking derivative of 5x minus 2, derivative of 5x. That's 5. Okay, then I have the second function unchanged, so x squared plus 1 minus first function unchanged, so 5x minus 2. And then right, I'm here. Let me show you. Something's missing, right? So that needs a derivative. Okay, so derivative of the first one times the second unchanged. First unchanged, derivative of the second one. All right, so 5x minus 2, that was that unchanged. Now derivative of the second one, x squared plus 1, so that's just 2x. And We don't necessarily need to simplify this, but let's actually do it. Just as a, just review. So that equals. So 5x squared plus 5 minus, right now I'm distributing, multiplying, whatever you want to call it, right? So this and this. So that's going to be 10x squared, or let's do it this way. So in parentheses, right? Because I want to keep that negative out. I'll need to deal with it at some point, right? But let's multiply it first. So 5x times 2x is 10x squared. And then we have negative 2 times 2x, so that's 4x minus 4x. Okay, and then let's leave the bottom like this, x squared plus 1 squared. Okay, so I have 5x squared plus 5 minus 10x squared plus 4x divided by x squared plus 1 squared. Okay, and then the final answer, and we can combine these two, so negative 5x squared. Something is missing here, square, plus 4x plus 5, x squared plus 1 squared. Okay, so this is the final answer. Okay. All right, so yeah, I'm gonna give you a bunch of problems to practice, and now let me just show you a little bit, a bit of a pitfall. It's not really pitfall, but all right. So let's say again, right? We're trying to find the derivative, and we have something like this: d dx, and we're taking derivative of x cubed and plus cosine x, and divided by 6. Okay, so yeah, you can use the quotient rule, but as you probably saw, quotient rule is quite labor intensive, and kind of it's just difficult, right? So rather than looking at this as a function where you divide by another function, well, g of x equals 6 is also a function, but it's just a constant. So we can look at it like this. So d dx, right? And now what I have is that 1/6 and then times x cubed plus cosine x. Okay, so I just take derivative of that, just a regular derivative of those two terms, right? Of these two, of this one and this one. And 1/6 is just a constant there. So again, right? So 3 derivative of x cubed is 3x squared. So I'll have 3 over 6, right? X squared. And plus, let's just keep that 1/6. And this is derivative of cosine x is negative sine. So negative sine x. And yeah, let's simplify a little bit. So we have half x squared minus 1/6 sine x. All right, so this is the final answer. Okay, and here are a couple of problems for you to practice, so problems. Make it regular white. Okay, so the first one is, so you guys are just taking derivative, right? Derivatives of all of those functions. So the first one is x cubed times cosine x. Second one, f of x equals x squared plus 3 times x squared minus 4x. Yeah, so in this one, you can of course multiply it out, right? You can FOIL it, and then you'll have just a polynomial to take a derivative of. But right, the point here is to practice that product rule. Okay, number 3. Okay, so number 3 is like this. So this one, it's a quotient, so sine x on the top and x squared here. Okay, so number 4. Number 4 is 10 over 3x cubed. Okay, number 5. That's the last one. X divided by x squared plus 1. Okay, so 5 problems, and here are the answers. So the first one, I hope I can fit them in here. Yeah, I can. First one is x squared times 3 cosine x minus x sine x. Okay, then the second one, this one is 4x cubed minus 12x squared plus 6. I don't know, there's some minus 12 floating in my notes. I'm not sure where it belongs. Yeah, so I hope you guys get the same answers. I'm not sure what that minus 12 is. Anyway, so the next one is x cosine x in the numerator minus 2 sine x and divided by x cubed. All right, the next one is negative 10 divided by x to the 4th. And the last one, I hope these are right. Anyway, 1 minus x squared divided by x squared plus 1 squared. Okay, so let's look at other trigonometric functions, namely tangent. Okay, yeah, so other. Trigonometric functions. Okay, so yeah, let's take a derivative. Let's try to figure out what the derivative is of tangent. So let's just name it example 1. And we need to do derivative of tangent. And yeah, tangent is sine over cosine. So we have sine on the top, cosine x. And yeah, this is, we need to use a quotient rule. So it's a derivative of the top. Maybe let's use parentheses. So sine x derivative times cosine x. Then we have minus. minus. Yeah, I was thinking about extending that. Oh shit, don't have space. Yeah, let me try to squeeze it here. So we have minus. Now we have sine x times derivative of cosine x. Cosine x and derivative of that. And the bottom is cosine x squared. Or cosine squared x. Okay. So yeah, we have derivative of sine, so that's cosine. So I'm just going to write cosine squared x. And now we have minus, and it's a derivative of, what do we have here? Sine times cosine x. So sine x times derivative of cosine x. Derivative of cosine x is negative sine x, so we have plus sine square divided by cosine square x. Okay, so I hope you guys remember a couple of those identities. So sine square x or cosine square x plus sine square x is just 1. Okay, so we have 1 over cosine square x, and this is secant square x. And so that's derivative of tangent. Okay. So let's write it down actually. So it's pretty important result. So tangent x, derivative of that is secant square x. Okay, so we have other derivatives, right? I'm just going to not really calculate them. You can do it yourself if you want to. d dx of cotangent x. That's negative cosecant square. Okay, then derivative. This one is important. Well, quite important. Derivative of secant. Okay, so we have secant x times tangent x, and then derivative of cosecant x. Okay, so this one is negative cosecant x times cotangent x. Okay, so I think the most, right, so this one is the most important. And then second most important, that you guys will see quite often, is this one. Okay, the derivative of secant. Okay, couple examples and then couple problems for you to do. So the first one, this is, I think this is example 2. If I remember correctly, so we need to calculate derivative dx, 3x minus tangent x. Okay, so derivative of 3x is just 3, and now we have that, right? We use this result from this calculation. So that was derivative of tangent is secant square x. Okay, another example, example 3. So this time we'll have to use the product rule. Right, so that's derivative of the first function. So the first function is x, so derivative of that is 1 times secant x. Okay, now I don't see the. Okay, and then we have plus x times derivative of secant x. Derivative of secant x, right? It's up here. Right, it's this one. So secant x times tangent x. And I don't know, we can't really simplify it, but let's factor that secant x out. Sometimes it's useful, if you have something in the denominator, right? Maybe we could cancel those secants, but at this point in this particular example, there's no denominator, but it's good to get used to factoring those common terms out. Okay, so that's the final answer. And yeah, let me give you a couple problems to do. So for practice, okay, how about, so calculate derivative of, this is actually just a function, not derivative. So x squared tangent x. Okay, and then the second one, it's secant x over x. Okay. Yeah, so the answer for the first one is, so this one is x times 2 tangent x plus x secant square x. All right, and the second one is secant x, and then in parentheses x tangent x minus 1 divided by x squared. Okay, so we've been taking derivatives, right, of various functions, and when you let me give you just a simple example of what's coming. So if I take f of x, and then take a derivative of that, f of x is x squared, so f prime of x would be 2x. But then I can keep taking derivatives, right? So that next one would be double prime, right? And that'll be 2. And then the next one, triple prime would be 0. Anyway, so let me give you maybe a different function. So this is called higher order derivatives. And yeah, so let's do just one example. Let's start with x to the 4th. Okay, so x to the fourth. First derivative would be 4, right, times x cubed. Then the second derivative, this is double prime here. Right, so the 3 goes to the front and we just keep going, so 12 x squared. Then third derivative, that would be 24, 24x. Okay, so 24x. And then after that, right, we have the double prime, then triple prime. And then when we take the fourth derivative, I write 4 in parentheses of x. Right, it's going to be 24. And then the fifth derivative, 5 in parentheses. Let me try to write it better. Okay, this one. So one more time. So 5, fifth derivative. I don't know if it's better. Now it's better. Okay, so a little 5 in parentheses above that f. And that's 0. Okay, so a couple problems for you to do. Okay, first one. So find second derivative of 4x to the power of 3 over 2. Okay, so that's the first problem. The second problem, let's do something like this. Again, right? So find second derivative of x divided by x minus 1. Okay, so yeah, let me give you the answers. So the first one is, the answer for the first one is 3. And then it's 1 over radical x. Okay, so that's the first one. And here, the second one, I have something like this. X minus 1 to the third. Okay, and you know, in a sense, you've seen an application of those, right, those derivatives. So when you have a, right, we had position function, right, so s of t, right, from physics. So this was position function. And then if we take the derivative of that, right, so s prime of that, s prime of t, that's velocity. So v of t, right, so velocity. And then the last one, double prime, t was acceleration, right, so a of t. Okay, so this was acceleration. Okay, so I don't know, let's, why don't you guys try to calculate that second derivative of that position function of a free-falling object. So that was half, we've done it before, right? gt squared plus v0 of t. And so initial velocity and initial position. Okay, so yeah, pause the video, try to figure it out, try to do it without looking. And yeah, so if we calculate that, right, so the variable is t is our variable, right, so that's what we, g is a constant, v0 constant, and s0 are all constants. Okay, so we take that 2 to the front, right? Subtract 1. So we get 2 over 2, right? Then g times t. And then this is plus, by the way. This looks like t, another t, but it's just plus. Okay, and then I have v0 times t, so plus v0. And then derivative of a constant is just 0. Okay, so that is the... Let me rewrite it and get rid of that 2 over 2. So that's just gt plus that initial velocity. Again, this is plus. This is not t. Okay, so acceleration, so as double prime. I'm struggling with this double prime of t. Okay, so we're here. Right, so derivative, if t is the variable, then derivative of that is just g. And derivative of that v0, right? That's a constant, is just 0. So let me hold on. Let's do it this way. So that's a of t, right? So acceleration function. So that equals g. And right, that's the acceleration of a free falling object, right? Just this gravitational constant. Yeah. So this was that gravitational constant. No constant. The value I remember is the international value. That's 9.81 meters per second square. Okay. Okay. Another application of those higher order derivatives is differential equations. So let's write differential equations are a topic in calculus 2, but we could do a couple simple problems. Quick look at differential equations. Okay. And yeah, I have an example, and it goes like this. So example 1. So we need to show that y cosine x satisfies the differential equation. I'm going to write dE, okay, for differential equation. And differential equation is an equation that has a derivative in it, right? So I don't know. Let me give you a couple examples just here, and then so it's like a side note. Right? So something like this, like y prime plus 6x equals y. Okay, and be a differential equation. Or dy dx plus 7x equals, for example, the second derivative, right? Second derivative we would write like this, d, and then square up there, y, and then dx square. Okay, so that's the second derivative. First derivative, second derivative. This looks like f. This is actually 7. But it doesn't matter. This is just some random example. Oops, that's not what I meant. Okay, so this was initially, I said 7x. So yeah, let's keep it at 7x. Anyway, so let me give you that differential equation that we will have to check. So y double prime plus y equals 0. Okay, so yeah, the second page, and let me rewrite this stuff. So solution, right? Or let's start with the equation. So that differential equation looked like this. By the way, when you solve a differential equation, the solution is not a number, right? The solution is a function. So this is the equation, double prime plus y. And this is the solution. So that was y equals sine x. And let's say you have, again, right, like a little bit of a side note. Let's take just like something like this, like 2x minus 4 equals 2. Okay, so this is just a regular equation, and we need to show that 3 x equals 3 is a solution, right? So, well, how do we do this? Well, we would take 3, right, and plug it into the original equation. Okay, so we don't know how to solve, right? We could also solve this, right? We could solve it and show that x equals 3. But in our case, right, we don't know how to solve that differential equation. So the only thing we can do, we can show that whatever they gave us is the solution of that. Anyway, so let's finish this one. Right, so I would have 2 times 3 minus 4 equals 2. Right, so we have 6 minus 4 equals 2. So yeah, it works. Okay, yeah, so we'll do the same, exactly the same thing over here. Well, but what I have here, right, so I can take that sine x, this is my y, and I can plug it in here. Right, but I cannot plug it in here because this is what I need. Excuse me. What I need is a second derivative. Well, so I need to find that second derivative, right? So this is my original function, right? So I'll do y prime of that, and then y double prime, and then I'll be able to plug it in here. All right, so let's do that. So I have y prime. So sine x, derivative of sine x is cosine x. So this is my y prime. Now the second derivative. So I have cosine x, right? So the derivative of that will be negative sine x. Sine x, okay. Yeah, so now I have it, right? So I have that double prime, so I can plug it in here. Right? So I'll be plugging that negative sine x in here and plugging that sine x over here. All right, so let's do that. So I have negative sine x plus y, which is sine x, and that's supposed to be 0, and it is. Right, so negative sine x plus sine x is 0, so y equals sine x satisfies our differential equation. Okay, so this is the answer. Okay. Okay, so let me talk a little bit about that, about the notation. Okay, so another side note. So let's say, right, we have a differential equation, dE. It looks like this. We can use the one that's above there, but with a slight change. Let's do y prime equals, let's just do 2y. Okay, so I changed that y to y prime and the 0 to y. So it's just a random example, right? I'm not like taking it from anywhere. So now right? So that's one way of writing this, and maybe that's better, but sometimes we would write it like this. I showed it to you before, right? So then to indicate that this is the second derivative, we would write it like this. And then dx squared, right? So that would be second derivative plus the first derivative, so that just dy dx. And then here is just 2y, right? That doesn't change. Okay, so that's second derivative. We show it by putting a square there and then right there. Okay, just wanted to show it to you. And yeah, the next thing, I'd like to give you a couple, just to remind you about very important type of problems. So the first one is finding that that those points where a graph has horizontal tangents. So let's call it example 1. So let's write it properly. So let f of x equals x to the fourth minus 2x squared plus 3. And so that's the function. Find points where the tangent lines, or tangent lines, where something's not right here, where tangent lines to the graph are horizontal. Okay, so basically, right, what does that mean? Well, we have a, that's not really the graph of that function, because I want to do it later in a moment. Let's say we have a graph, right? So those tangent lines that are horizontal would be right there and right there. Okay, so these are the points we need to find. And yeah, keep in mind, right, that slope, right, of a tangent line to the graph at certain point is basically is a slope, right? Well, slope is a slope, yeah, of course, but yeah, so slope is a derivative, right, or a formula for slope, right? So derivative is either a slope, right? If we are given a point, then we can plug in that point into the formula. If we're given a line, right, then derivative is just a slope. And let's just do the problem. I don't know. I hope what I'm saying makes sense. Okay, so now we have those, right? We have this equation, and we need to find its derivative, and then make it equal to 0, right? So f prime of x equals 0. So let's find the derivative first. Alright, so we're here. So derivative of x to the fourth will be 4 x cubed, right? And then minus, right? So now I'm taking derivative of this. So that is 4x. And then lastly, derivative of 3 is just 0. Okay. So now, right? We don't have any specific. So we found the kind of the formula for a slope, right? And this point, we don't have those. At this moment, we don't have the points, right? So we need to find the points where that slope is 0. So derivative needs to be equal to 0. So we have that 4x cubed minus 4x equals 0. Okay, so factor for x. So we have x squared minus 1. Okay, equals 0. So now we just need to solve it for x. So factor that x squared minus 1, so x plus 1, x minus 1 equals 0. Okay, so it looks like we have three zeros and 3 solutions, 3 x's. So the first one comes from this x, right? If I plug in 0 in there, I'm getting 0 at the end, so 0. Then the second, x equals negative 1. This is 1. And the last one, that comes from the last factor, the last parenthesis, x equals 1. Okay, so now we have 3 zeros, 3 x's that will give us those 3 points. Now what do we need to do, right? We need to figure out what those what the y's are, right? So we have the original equation, which was f of x. And if we're trying to figure out what the point is on a graph, we just take x and plug it into the original equation, right? Minus 2x squared plus 3. Okay, so I'm not going to do it, right? It's just simple arithmetic. Plug in 0, right? In for x's, and then negative 1, and then 1. Right, so those points are, the first point is 0, 3. Second point, let me make this semicolon again. Right, so this is 1, 2. And the last one is negative 1, 2 as well. Okay, yeah, so at those 3 points, right, the graph will have horizontal tangents. And now let's make a proper graph. Okay, so I hope you guys still have those points. So the first one was 0, 3. Okay, so that's this one. Then we had negative 1, 2. Okay, so this one. Negative 1, 2. And then the last one was, where's that point? Let's make it different color. So blue. And the last point was 1, 2. Okay, so something like this. And the graph, I'm just going to go over those numbers, right? The graph looks something like this. That's a quartic function. Okay, so it does go through this point, right? It looks like it doesn't, but it does. Right, so you see those, I hope you see those horizontal tangents. Right, here. Yeah, so just kind of I'm trying to emphasize that the fact that that the derivative is related to slope. Right? It's either slope, so derivatives gives you either slope or formula for slope. Okay, let's do another example. This is example 2. And it goes like this. Another function, let f of x equals 16x divided by x squared plus 16. And what we need to do, find, so this is, this should be a period. And then we need to find equation of a tangent line of a line tangent to the curve, at the origin. Okay, so again, right, we need to find the slope. So slope is related to the first derivative. So we'll calculate the first derivative. So f prime of x. So this is a pretty simple calculation. I mean, it's not simple, right? It's just quite laborious, right? So, yeah, it'd be good. Maybe at this point, you guys could write that the formula for first derivative for quotient, right? Quotient rule. Yeah, so pause the video, try to write it on your own, and well, it goes something like this, right? So we have derivative of the top. Right, so this is, let's see. Right, so this is going to be f of x. This is going to be g of x. And this shouldn't be f prime of x, right? So maybe actually let me delete it. And let's write just dy dx. Okay. Right, so, and yeah, we could change this to, maybe it would be better to change this to y, but anyway, so I hope you understand, right, that f is going to be the top function and g is going to be the bottom function. So f prime of x times g of x, I'm just writing the general formula, minus f of x times g prime of x. Okay, and the bottom is g of x squared. All right, so we have the formula, so let's do that calculation. So equals, right, so we're doing the first derivative of the top, right, so 16x, so that's just 16, times the second function, the bottom function unchanged, so x squared plus 16, and then I have minus, top function unchanged, so that's going to be 16x, times derivative of the bottom function, so that's going to be, bottom function is here, right, so derivative of that would be 2x, and then we have x squared plus 16 squared. Okay, so we simplify it, right, and we get something like this. 16x squared plus I'm just looking at it, I think it's right. Okay, plus 256 minus 32 x squared. Right, so obviously we can combine these. The top, the bottom is x squared plus 16 squared. Okay. All right, so I don't know. let's combine these two terms. So these two, right? This one and this one. All right, so combine these. So it's going to be negative 16x squared. So equals negative 16x squared plus 256. And then the bottom is x squared plus 16 squared. Okay, so at this point, what we have is a, let me write it actually. So this is a, right? So what we found is a formula for slope, right? In a sense, first derivative, right? So formula for slope. So now we need to find slope at the origin or at 0, 0. Right? So I take that f prime, right, the first derivative, and I evaluate it for 0. So what we get is 1. Okay, I'm not going to do that calculation. Right? I hope it's simple for everybody, and that is exactly the slope, right? So m. And that's not the final answer because, well, let me erase that actually, if it's not the final answer. So we need to find the equation. And then we can use this, right, this point slope formula, y minus y1 equals m x minus x1, not 1, x1. Okay, so we'll use this point, right, this to give us our x1, y1. Okay, so we have y minus 0. Slope was 1, x minus 0. So we get y equals x. So that's the equation of that line tangent to the graph at the origin. Okay, so yeah, to finish the problem, let's sketch a graph. Okay, this is what I have in my notes, right? I think the graph I hope it's right. Anyway, so here's the graph. It goes through the origin. Okay, and I think it keeps going. You guys can check it, I'm not sure. And you see that, right? So now origin is right there. And the tangent line, right, will be something like this. Right, so let's write the equation of it. Y equals x. Okay. Yeah, so this is not perfect here, right? But yeah, it's good enough. Okay. Okay, so a couple problems for practice, and yeah, that'll be it. So practice, let's write actually problems. Maybe I'll start using a different color for this problem, for this practice. What color? Maybe red. Okay, so problems, and then I'll switch to regular. Alright, so the first one is that finding that equation of a line. So find an equation of a tangent line, or of a line tangent to the graph of f of x cubed plus 4x minus 1. I barely have enough space. X minus 2. And then at 1 negative 4. Okay, so this problem is slightly more difficult than what we just did. But I hope you can, I think you can handle it. Okay, and the second problem is the same. So the same, find equation, and then the function is like this. So we have x minus 1, x plus 1, and it's at 2 1/3. Okay, and then the third problem. So verify that y equals 1 over x, where x is greater than 0, satisfies a differential equation that looks like this. This looks like an interesting problem. So x to the third, and then you have y double prime plus 2x squared y prime equals 0. Okay, so let me give you answers. Yeah, so the third problem, yes, it does satisfy, so you need to show it, you need to prove it. First problem, that equation looks like this: y equals negative 3x minus 1. And the second equation, or second solution, or solution for the second problem, is 2/9 x minus 1/9. Okay, yeah, so that's it. That's the end of that lecture. And yeah, I'll see you during the next one.